In this lecture, we will be talking about classification techniques for data analytics. Classification is a task of learning a target function f, which we will also call a classification model, that maps each attribute set x to one of the predefined class labels y. So we have an input from our data, we have attribute set x, and this attribute set x is analyzed by the classification model f, and its output will be a class label y. So, for example, we can see here the table of various data entries of various life forms, various animals. And we can see their characteristics, such as that the body temperature is warm-blooded or cold-blooded, whether they have skin-covered types of hair or scales, or whether they give birth to their young ones, or whether they lay eggs, whether they are aquatic creatures or not, whether they are aerial creatures, whether they have legs or not, and whether they do hibernate. And all these attributes can be used to predict whether a particular new animal will become is a mammal, or it is a bird or a fish or a reptile or an amphibian. The learning is typically based on a data set with a collection of records. So typically we would have such a data set as an input for learning process, which will learn the target function f, our classification model. And then we will have in that data set, each record is already characterized by a tuple of attributes and the class label, as we can see here. And then we can use this classification model either in the context of descriptive or predictive modeling in data mining. By descriptive modeling, we mean that we are able to, given a certain known class, can explain why a certain type of animal is belonging to a certain class. And the predictive modeling is where we do not know the association to a particular class, like, for example, what is the class of animal known as Gila monster, and we will use our classification model and the attributes of this new test object to classify it into a particular animal class. Classification primarily deals with categorical variables which are of nominal attribute types. So that is the target value we will be associating our test entries with. It is less effective for ordinal categories like small, middle, and large, which are also of qualitative type, but they have a certain sorting. The most classification techniques do not consider order, and therefore they do not really differentiate between small and middle and large. They treat it as three different categories without the relationship of an order between them. Similarly, hierarchical relationships such as superclass and subclass are often ignored. So if we have aspects such as the animal, and then we have a mammal, and then under the mammal we will have four-leg mammal. All these kind of hierarchical relationships and classes will be not really subject of our study of classification technique this time. We will more look at classifying data with binary or nominal categories. Then we will look at various techniques how to build a classification model. We will discuss the so-called nearest neighbor techniques. We will talk about rule-based methods, decision trees, and we will not cover techniques like naive Bayes, support vector machines, linear models for classification, or neural networks, because those are already techniques which are based on probability, and they will be well covered in classes on machine learning. So the machine learning uh, um, domain of classification will be not covered within this lecture. Generally, we can see that a process of classification has several stages. One stage will be that we have a training set where we can see here that there is some kind of a data entry, and then we use the induction in order to learn a particular model. For that, we will be using some learning algorithm, like are those which are listed here, so that we capture the model, learn the model as a process, and then we have that model for the classification. At that point, we can have any other input model, data entry coming in, and to be evaluated by that model. The model will be applied by and by a process of deduction, we will uh, determine the classes of our test set. So often we will have a kind of a test set and a training set, which we will be talking about. And this test set is also often used in training. So in training, we will have just a training set, which is our kind of a basis set of objects and attributes. And then, but we are not only interested whether the performance of the classifier is good in these entries, but we also primarily want to know whether it generalizes, and therefore we will need to test our capability of the model on the test set. So in fact, this is a training loop, you could say, where we are after we evaluate with the test set, we will then perform certain maybe modifications to our learning, or control the learning process or stop the learning process based on the test set outcome, and also training set evaluation. But then once the training model is completed, we can use it for the classification purposes. And in most of the techniques which we will be discussing, we will no longer be using the training set, or we do not need to store it anymore. The only thing which we need to store is the model, so that we can apply it on the new type of data and classify it. Classification has a very broad application possibilities. Generally, it is related to tasks like, for example, recognition. We can, in the previous example, we were able to classify various animals types into the animal groups, such as mammals or birds. But this is just an illustrative example where you can find the usage of classification will be, for example, in handwritten recognition. If you are writing digits and you want to automatically recognize which digits have been written, you would have a classification technique that will classify each of your digit of handwritten into set of digit classes, naturally 10 digits in the decimal system. But that is just yet another example. In medicine, you might be interested to classify the imaged tissue by various types, such as maybe bones, maybe some organs, maybe some pathologies, which the doctors are interested to identify in order to establish a treatment plan. And in sciences, there will be a classification used, for example, in maybe weather measurements, meteorology, where we want to identify a formation of hurricanes, classify a cloud formation, whether it is on an increasing trend towards building up a hurricane or several other use cases. So, and for classification to understand how it performs, we need to have some kind of evaluation of the classification technique or model performance. So this performance is based on how correctly and incorrectly are predicted the test records. That we can summarize in the so-called confusion matrix, which characterizes whether the model performed the classification well or not. Simply imagine that we have a set of records where we know the outcome. So this is also known as a supervised approach, supervised training in general, or supervised classification techniques. And we know the class. Here we have just two classes, binary class, two-class classification. And we have the actual class where we know that the data object is it belongs to the class 1. And then we have a predicted class. And then we can measure how many times we have actually it occurred to us that we have correctly predicted class when the class was class 1. Then similarly, we have also for the actual class 0, we can observe in this confusion matrix the correct prediction has been performed this and this many times with the classification algorithm on the entire set of test objects or test records. And this is also correct classification to the class 0. And then we have the incorrect classifications, like for example, this one, where the class is actually class 1, but it has been wrongly predicted as class 0. And here we will be counting. This is the frequency of our occurrence of the incorrect classified data entries, which have class 1, but have been classified with 0. And here we have the reciprocal case or analogous case where we are predicting that the class is 1, but in fact, the true class of that data object was 0. And again, we are counting how many of such occurrences are appearing. And from this confusion matrix, we can build the characterization of accuracy or error rate that are used as performance metrics. So accuracy would be a fraction of correctly classified cases to all cases. So we have a number of test records, let's say 100, and maybe we have correctly classified class 0 as 0 20 times and class 1 as class 1 40 times. So we will have 60 in total, divide by 100. So we will have 0.6 accuracy. In the same scenario, in the same case, we can talk about the error rate where we have the incorrect classified cases. And if we stay with the same numbers, we can say maybe we have 20 cases where we have the incorrect classification of that the class was wrongly predicted as class 1, and here where the class was wrongly predicted as class 0. So we have 20 and 20, so this will be 40 divided by 100, as we described before, will be 0.4. So the error rate will be 0.4 in this case. So these two are important metrics which are characterizing the performance of our classification model. We will start our discussion about specific classification technique with the nearest neighbor classifier. or we also refer to it as the KNN. K means that we are interested in K nearest neighbors. So let's start describing how this technique works. This technique is a very simple classifier. We start with the so-called Roti classifier technique, which is an approach that memorizes the entire data set, and the test instance must match the training instance. So it's essentially just like a database query and this Roti classifier, where we will just be able to uh, uh, query a certain existing record, which we can call the training set actually. And if in that training record if the training record exists, then it will return the class for that training record entry. So it's actually not really learning anything. It's just memorizing the entire data set and acts basically as a database query. So, but this is a very simple classification technique, but doesn't really do much of a classification. Uh, but to this technique, nearest neighbor is somewhat related, that it actually and inputs into the model an unknown record, but the algorithm of nearest neighbor will be uh, returning a class of which is dominant in the neighborhood of the unknown record. So we have a training set which is somehow spanning a multidimensional array of its attributes. So here we will have like a two-dimensional array of two attributes where we have some classes categorized as plus and some classes categorized as minus, positive and negative. And now we have our unknown record, and it has attribute one attribute has this value, another attribute has this value, and the question is, are we now positive or negative? And based on this neighborhood, the nearest neighbor classifier will say this unknown record belongs to the class positive. So it is based on adoption of class of neighboring samples from a set of labeled records. So from the training set. Now, we can see this technique as a parametric technique because it has a parameter k, which determines its neighborhood. So the parameter k determines the number of nearest neighbors to retrieve. So it is based on some distance to our uh, new unknown record, and we are measuring in the parameter space or in the attribute space distances to other known training records, and those which are the closest, the k closest, will form the um, the basis for decision making. What class is the unknown record classified with? So the parameter k determines the number of nearest neighbors to retrieve, and therefore, in order to define nearest neighbors, we need some kind of proximity metric, which computes the distance between our unknown record and the known records in our data set, in our entire training set. So that could be as a Euclidean distance, or it could be some other distances, which we have already talked about. So the this proximity metric, therefore, is used in the selection of our neighbors around our unknown record. A slightly different technique, which I will just mention very shortly, is a technique which has a which is based on a radius of from an unknown record. So another parameter could be to define a proximity radius, which will be defining some kind of a multidimensional ball in the attribute space, and then all the records which are within the ball, proximity ball, will be used for categorizing the unknown record. So this is another approach which could be used, and that one is more related to techniques which are known as kernel-based methods. So we will not be talking about the kernel-based methods, but I just want to uncover that there is a tight relationship between the k-nearest neighbor classifier and the kernel-based methods. So with this, we will now dive deeper into the nearest neighbor classifier characterization. So in case if our nearest neighbors belong to the same class Y, all of our k nearest neighbors, the test instance is classified to belong to the class Y. For example, we can see that here, where we have again some negative classification, some positive one, and now we have our unknown record here, and it has just one nearest neighbor, and this one nearest neighbor is negative, therefore it will be classified as negative. But if we change the parameter from one nearest neighbor to two nearest neighbors, then in such a case, we will have two nearest neighbors, and here we have negative and we have positive. So now what we'll do in this case? If there is a mix of classes, yi, test instance is classified by majority vote. So, but in this case, the majority vote is not really deciding because we have no majority. But therefore, there is also another aspect which can be considered, and it's probably also intuitive, that if we have the unknown record here, it is clearly closer to the negative class record than the one which is in the neighborhood classified as positive record. So therefore, we can employ some kind of a distance weighting factor, which will be influencing the majority vote. For that, we have a equation here where we can see the nearest neighbor classifier is defined from the sum of the by the majority, so argument max of V, so this V are the various classes, and the one class V which has the most of the classes occurring, so this function I is basically just counting for each class how many classes there are, but it is also weighted by the distance. So each instance of a record, each count is weighted by the distance. So in that, the closer ones will be counting more than the ones which are more far away within the neighborhood. So with this, we will be able to make a majority vote decision where we will be seeing that the class here is getting will be the majority vote with this weight will determine this unknown record as being the negative, belonging to the negative class. The situation for three-class neighborhood will become a little bit more unclear again when we have these two positive votes and one negative. If we do not employ the weights, then clearly the positive neighbors will have a majority vote for the class membership of our test record. However, if we employ this this distance approach, it might be that this distance, which is a reciprocal of squared of the distance of the Euclidean distance, for example, we might this record, which is fairly close, might then overrule the vote of these two other neighbors and might still become the majority vote. We can see that the classifier on the previous examples is quite sensitive to the choice of k. The small k is often in hazard of being sensitive to noise, while the large k might sometimes smoothen important details. Therefore, this parameter needs to be selected with care. We can see an example of a problematic selection of the k in this image, where we can see that the unknown record, which is selected, is surrounded by a very small neighborhood of the positive classes, while the negative classes will be probably dominating the largely selected neighborhood of k records, and probably this unknown class record will be classified as negative, which would then mean that this detail of this positive little island will be essentially not visible in the final classification. However, if we would apply the weighting aspect into weighting each neighbor by its weight by the proximity, maybe the positive values will still be able to be retrieved, and this record can be classified as positive. So that gives us the possibility, the weight, to somehow be a little bit less sensitive from this parameter. Now, we will be talking about decision boundaries also, especially later in the case of decision trees, which, because those decision boundaries are rectangular, here, as opposed to the later examples of classification techniques, the decision boundaries are formed by an arbitrary shape, as we can see here. This is the so-called Voronoi diagram. You might have heard about it before, and it basically associates with each point a certain area around that point, to which every point within that area is closer than to some other point. So if we look at this point, for example, is closer than to this point. And here we can see that there is a certain boundary. So this point will be here closer to this point, but behind this boundary, this point will be closer to this point. So this kind of Voronoi diagram representation, which can be geometrically relatively easily calculated, will be a typical nearest neighbor classifier decision boundary if we have a k equals 1. So for k equals 1, once we enter one of these partitions, we will immediately know to which of these elements the class belongs to. And that could be, for example, used for in some kind of optimization, because you can imagine that if we have many entries, this might mean that we will have a lot of processing to go through all our data records from the training set to be able to find out what are the nearest neighbors. So clearly, for that purpose, we would need some kind of acceleration structure, which will be able to deliver us much quicker access to the neighbors around a particular spatial location. For that, various types of techniques are used, like the KD trees, for example. We will not cover this performance detail in this lecture, but it is important to keep in mind that for large data records, the KNN will work very well, will be performant only in case we have a very fast spatial structure, which can tell us about the neighborhood of a certain position in this attribute space. Keep in mind that this attribute space might be quite large in terms of attributes, and that might put additional complexity on the algorithmic implementation. Now, it is important to mention that nearest neighbor classifier is actually not really learning anything because there is no model which is being created from the data set. Actually, the data set itself is the model, and therefore we do not need to reserve any time associated with the model learning or training because the model is the data set itself. However, uh, the toll, if you like, comes with the time when the classification task is about to be performed, and there some techniques which have the model explicitly created from the dataset might perform much faster than the nearest neighbor classifier, which will need to find all the k neighbors around the neighborhood. And in the naive version, we'll need to go through all the data entries to determine which of the neighbors are the closest. Now, that is classifying this nearest neighbor classifier into the category of lazy learner classifiers, which this is the only example which we will cover. And the next two, which we will be talking about, are the eager learners, which means that once the data set training set is available, we will create a model which will be then used for the classification task. And this model will be learned early and not late, as in the case of the lazy learner. It is also important to state and characterize that the nearest neighbor classifiers are might occur problematic when our attributes in the attribute space of our dataset significantly vary in spread and scale. So you can imagine that if we have a certain record, maybe medical record of persons, then we can have, for example, height defined in meters and weight defined in the kilograms. This will be a very typical scheme in characterizing the properties of human body. Now, we can see that height in meters is not probably varying too much. It's probably varying something between 1.5 meter to 1.9 meter in the most of the cases. And while the weight might, for 1.5 tiny female, might be around 45 kilos, while for a 1.9 meters tall man, obese man, might be even 150 kilograms. So we have a spread between in meters 1.5 to 1.9, while for the weight we have a spread of let's say 45 to 150, so which is much larger spread. So if we have such a situation, that might become a problematic for our distance measure. Have a look at what might happen here if we use the Euclidean distance here, where we are basically performing the distance between the two measurements. So this will be two different, maybe this is the unknown record, and this is the one of the training entries. And we will have a given height for each of these records, and we will be squaring the difference in order to calculate our Euclidean distance. And then we have here for the other attribute. So we have two attributes, this and this is the weight attribute for the unknown record and for one of the entries from the training set. And it is squared, and square root is calculated out of this. And if we perform it on our attributes of height and weight, as I discussed. So here are similar numbers. Here we have 1.9 minus 1.6. This will be 0.3. And here we have 100 minus 60. This is 40. So 0.3 powered by 2 is 0.09. And 40 powered by 2 is 1600. We can see that this distance measure will be heavily dominated by the weight, and the height is actually not contributing to the distance measure almost at all. It's negligible, and everything will be basically determined based on the weight aspect. So we need to be very careful about this, and ideally the nearest neighbor classifier uses attributes which are standardized so that they are all put on some kind of a reparametrization where we have maybe zero mean and a standard deviation of 1. And in such a case, all of the attributes will be treated equally. We have to also make sure that if we have irrelevant attributes, attributes which do not have anything to do with the given classification, like, for example, we will be interested in whether the person is at health risk, and there will be an attribute of a color of a t-shirt of that person, which is clearly irrelevant, then this attribute might lead to adding noise, because we will consider the distance of our record of also between t-shirt colors, which doesn't have to do anything with a health risk assessment. Then we can also have redundant attributes, like, for example, the price and the associated tax, and then the total price. If all that is among the attribute of a transaction record, those attributes together will be biasing the proximity measure and will be giving it collectively a higher importance. And that needs to be considered. And ideally, before we perform the nearest neighbor, not only that we need to standardize the attributes, but we should also filter out all the irrelevant attributes, and also all the redundant attributes should be just represented by a single one. Our final comment on the nearest neighbor classifier will be related to the proximity measure itself. Sometimes the Euclidean proximity measure might be very useful, but sometimes it might not be the best proximity measure, and instead another measure might be much better. So let's have a look at, for example, the asymmetric attribute cases when we have, for example, some document records, and then in such cases, like here, we can see that we are having records of occurrence of a certain word, and in this document, that word, all these words occurred except of one. And here, similarly, many of these records words have occurred except of one. And we have other records where none of these words have occurred. And here we have another record where almost none of the words didn't occur, and here also. And we can see how is this similarity measure considered in case of the Euclidean measure, and as compared to the cosine similarity, which might be much more useful than the for the document records with asymmetric attributes than the Euclidean distance. So for Euclidean distance, and we know in case of asymmetric attributes, the attributes which have zero, there are many, many times zeros, because there are many, many words which are not occurring in the documents from all the possible words we can think of. And therefore, there will be mostly in these document record zeros, and only few times we will have ones. So it will be very sparse representation, although these two examples are not examples of that, but that will be generally the case. And if we are then in this record database comparing the two relationship between these two records, for example, it will be giving us that they are very similar. And but and we can agree to that because many of these words are co-occurring, so it might be very similar. So the measure will tell us that the Euclidean distance will be square root of 2. Why? Because we have here the dissimilarity is here 1 minus 0 squared is 1, but 1 minus 1 squared is 0, 0, 0, 0, 0. So if we perform this subtraction in the Euclidean distance from one record's attribute from another, this will be all zeroed out, and only these two values will be forming as the 1, 1 plus 1, and square root will be square root of 2. And guess what? The same thing will happen here. Here, the differences of zeros with zeros will be also contributing with 0 to the distance measure. And here, this will be contributing with 1. And also this one will be contributing with 1. So it will be also square root of 2, which means that in some sense, these two records are classified that they are have the same distance. However, we would probably agree that in the asymmetric attribute of text records or word records, document records containing the flag whether a word occurs or not, these two documents will be very similar. While these two documents, we cannot say whether they are similar, we can only say that they are um, uh, uh, their um, cosine. We can only say that only that two words which co-occurred were different words, and the other words which we see here, none of them occurred in this document. So if the words have been chosen in the context of transportation, let's say, and this document is about animal kingdom, and this document is about some financial aspects, then none of these two documents have anything to do with the words which we have been looking for typical documents from, but we cannot really say that they are similar. So actually, the cosine similarity will be much better measure in this case because it will tell us that the cosine similarity is here forming the value 10/11, so almost 1, while the cosine similarity here will be saying us that it is 0, meaning that this is not really good measure of a distance because it should be 1 minus this distance. But so these two records are very similar with the cosine similarity, while these two records are considered as completely dissimilar, and therefore the distance here will be very small between these two records, while the distance between these two records will be very high. So it is important to mention that here we have the smaller the better, because the distance, the Euclidean distance, is a distance measure, but the cosine similarity is not a distance measure because it measures a similar objects are having value 1 and dissimilar objects are having value 0. So here we would need to, in order to make it to a distance, here we would need to put like 1 minus value here and 1 minus value here, so which will mean that for that distance this will be close to 0, and for the distance here based on the cosine similarity this will be value 1. Now let's move to a different type of classifier, which is the so-called rule-based classifier. This is in some sense a complete opposite of the k nearest neighbors, which are purely based on the data set in order to classify an unknown record, the rule-based classifier doesn't use any data set on the classification task. It uses exclusively only a very compressed representation of rules, which will perform this classification task. So it is basically a technique which carries out a set of rules. If condition C is fulfilled, then Y, the object is classified with the class Y. And we are having a rule set R consisting of several rules, such that each rule will give us a formalism of whether a condition is fulfilled. If it's fulfilled, then the data record is classified with a particular class. So for example, here we can again see our example of various warm and cold-blooded animals, and coming from the animal kingdom of mammals, reptiles, fishes, amphibians, and birds. And now we can, for example, have a rule condition here where the rule is saying the condition is if it gives birth to its young ones, and at the same time the body temperature is warm, we will have this will become a mammal. Let's have a look. Human is a warm-blooded and it gives birth to its young ones. It's a mammal. That's correct. And then we will have a look at cold-blooded. Everything what is cold-blooded cannot be a mammal. It's not. Whale is warm-blooded and it gives birth to its young ones. It's a mammal, correct. Then a frog is, all these are cold-blooded. They are not mammals. Dragon bat is warm-blooded and it gives birth to its young ones, and it's a mammal. And notice that, for example, it is also an aquatic creature. The it's also an aerial creature, the bat, which would be most typical for birds, but it doesn't matter because this condition is not really testing for these aspects. It only tests two attributes in order to determine the mammals, which is sufficient in this case. And we can see that this will be fulfilled for a cat and for also for the guppy and the alligator are reptiles and fish and reptile. Penguin is a bird, doesn't fit, doesn't give birth to its young ones. Porcupine, it will be a mammal, and then eel and salamander will not be mammals. So this condition, this rule is simply for this type of data will be 100% correctly assigning the typical animal class to the various animal types. You can imagine that there could be some exceptions, like we have various animals from from Australia, which might be challenging this rule set in order to determine the animal type and or class, and therefore this might have a certain um, classification error in the real use. And this is also what will be defining somehow its performance measures. So if we have a data set, training data set D, and a classifier is based on a rule R, where we have a condition A and the class Y, the coverage is defined as a fraction of records in D that trigger rule R. So coverage is coverage of how many of the records are being covered by this rule R. and so we can see the number of elements in this data set which fulfill this condition divided by the total number of data. So in the previous case, we had human, we had whale, we had bat, and then we had cat, leopard, and porcupine, which will be fulfilling the condition which we had mentioned, and those will be counted in this set A as compared to all the animals which we had in the data set. That will be giving us the coverage of that rule. Now, the accuracy is defined as a fraction of records triggered by R whose class label is actually Y. So it might be that this condition A is fulfilled, and then the classification, rule-based classification, will classify that object, that record, as belonging to class Y, but it might be wrong classification in that particular case. And therefore, it might not satisfy the set of certain set of records, but for some set of records, it might work quite well. So we can see that here we have the amount of records from which are subjected to the condition A, and at the same time they are part of the class Y divided by all the records which are related or covered by this condition A. In order for the rule-based classifier to work well, it is important that the rules in R are mutually exclusive, so that we do not have two rules that are triggered for the same record, because then it will depend on in which order these records, these rules are, and the last one which will be executed will determine and override its class potentially. So we should have only one rule per record. The same record should not be covered by more than one rules. And it should be also exhaustive. So the coverage should cover all of the records such that each record is covered by exactly one rule. And if that's the case, then our rule-based classifier is both mutually exclusive and exhaustive, which are important properties for the classifier to work well. Now we will leave the classification of a rule-based classifier. Further details of this, how to build a rule-based classifier, are out of the scope of this lecture, and we will dive more into the so-called decision trees classifiers. Decision trees are similar to a rule-based classifier because they will build some kind of rules based on the attribute values of the of coming from the training set, but these rules are executed in kind of a hierarchical fashion. So it will be that we will make a decision which will be organized in kind of a tree, and based on the answer whether a certain attribute is having certain value or value range or not, we will either visit its one of its children or some other of its children. We can see it as also as a carefully crafted question followed up with answer, and further with another question and answer, which finally leads to the classification. So this decision tree is kind of forms somehow a structure of a dialogue, while the rule-based classifier is more of a type of single question with a lot of uh, specification, exhaustive specification for a record. So, and therefore, the organization of the uh, rules, if you like, into these decision trees might be easier to manage the mutual exclusiveness and exhaustiveness properties. So let's have a look how these decision trees work. We have here a case of some uh, loan applicants, and we have a training set. So we would like to know whether an applicant will likely not be able to pay off its debt for when applying for a loan. And here we have some previous cases of loan takers, and they have several characteristics, like whether they own a home or not, yes, no, yes, no, yes, no, whether they are single, married, or divorced. So, what is their marital status? What is their annual income? And whether or not they actually were able or not to repay their loan. And we can see that in this attribute space, we have attributes which are of categorical nature. This is actually a binary one. This one is a categorical attribute. This attribute is continuous. And this is the class which we are training for. So now we can, based on this training data, we can create the so-called decision tree, which will be the structure, the model based on which we will decide whether new data set, new entry, sorry, not new data set, new data entry will be likely to be will be to repay the loan or not. So first, we can see that from the homeowners, everybody who owned the home was able to repay the loan. So we can put the question whether somebody is homeowner. If somebody is homeowner, then they will not be defaulted borrower, meaning that they will be able to repay the loan. If they are not homeowners, then might be interesting to see what is their marital status. Based on this training data, maybe not generally applicable, but based on this training data, everybody who was married was able to repay the loan. Therefore, even if they are not homeowners but they are married, then these will not become likely the defaulted borrowers. The prediction will be that they will be actually able to repay the loan. But among those who are not uh, uh, living in a married status, those who are single or divorced, they might be some of them who were not able to repay the loan. So the single ones were not able to repay the loan, but not all of them. Some of them were able. But if we look at the income, those who earned higher generally were able to were actually becoming the defaulted borrower sometimes, but those who were having lower income, surprisingly, they were not among those who were those defaulted borrowers, like, for example, this person or this person or this person. We can see that, for example, this person who was divorced had has a very high income, but was not a defaulted borrower. But this case we already ruled out because in the top he is he has a homeowner and was able to repay the loan. So we can see that those who are not homeowners, are single or divorced, and have a high income are surprisingly a group which is susceptible to not to repay the loan. So now, if we have somebody who is not a homeowner but is married as a test data and with annual income of 80K, what do you think whether this person, according to this decision tree, will be able to repay the loan or not? Well, as married, seems to be the case that they will typically be able to repay the loan. So uh, uh, we can see here how we have the basis of the training data, which is used for building up this decision tree so that we can then perform the deduction of as a part of the classification process in order to find out what is the class of a new data record. And for the rest of the discussion about the decision trees, we will be also talking about how can we build such a decision tree and various other properties of it. So our main discussion now will be concerned with how do we build such a decision tree out of our training data, and how do we perform the various types of splits, and how is this possible for various type of variables. So let's start the discussion to describe the kind of generic and simple formulation of the Hunt's algorithm. Hunt's algorithm is a recursive approach to growth of the decision tree. You already know what does it mean, a recursive method, and we see that recursion has been often used in the case of search before in the trees, like for example in the backtracking. So let's use this intuition on how we will build this decision tree. So first of all, we have imagine that we are currently at a node of maybe already grown tree partially or at its root, but we are at a certain position. And at that position, at the node, we have a certain set of training records, DT, which are associated with the node T in which we are. And there are various classes of the records of Y1, Y2 to YC for all these class labels. Now, so we are currently, the D will be the entire training set, but now we maybe are already in some node where we already are dealing with a subset of our training records because some of them have been somehow rerouted to other directions of this decision tree. So we have a subset of records, and within the subset of records which are associated with this node T, we have various values of the classes for these records. In case the DT has only one class, YT, so not many as indicated here, but just one, then the T node should be a leaf because we already have a set of records which just have one class. Therefore, if based on the training process, if we reach this node, it should be decided that the new record will be obtaining the value of the class, which should be the YT. And in case the DT is a multi-class training records set, meaning that several of these classes are still present, we can select an attribute test condition to partition the records into two or more smaller subsets, and then child nodes will be created for each outcome of the test conditions such that all records of the DT will be distributed to children based on the outcome of the test condition. So, for example, like we had before, this test condition can be yes, no. This test condition can be smaller than some value or larger than some value, or it could be several test conditions, like, for example, something like different colors or different categories of some possibilities, maybe up, down, left, right, could be some possibility in some kind of imagined scenario. So in this case, we are not done yet with our leaf and we have to generate the children. And let's now talk about how this generation should be done in the couple of the next slides, step by step. So for the build-up process of our decision tree, we need to somehow have some kind of attribute selection quality measure. Because we can imagine, here we still can see these parts of this table, we have several uh, of our columns here. We have the ID, we have the question whether they are homeowners, what is their marital status, what is their annual income, and here is the class. So what we know for sure is that we should not take this attribute of the class because that is not the part of the decision tree, that is the answer of the dialogue this decision tree somehow establishes. So probably we should also not take the ID because ID doesn't carry any information and should not be part of the candidates for an attribute normally. So we can still start with, let's say, the question whether somebody is a homeowner, somebody, what is their marital status, or what is their income. So, and then once we perform, let's say, a decision tree, so this is a decision tree which just contains the root, and it's still, in this moment, it's a multi-class node. This will contain the entire data set at this point, and most of the classes are associated, class outcomes are associated with no. So we will have an voting scheme here, and the maximal of our class occurrences will be basically determining the outcome of the decision tree. So based on the root-based outcome, so we didn't actually choose at this point any of the attributes, if there is to our first level or zeroth level model the, the new record coming for classification, we will just give it a classification no, regardless of what are the properties. Now, at this point, we can choose one of the properties, and we will discuss how do we choose that in the next, but we choose one, let's say the homeowner. Then we have chosen, and on one side we have whether somebody is homeowner, yes or no. And in the case that homeowners are we know that no homeowner was actually defaulted in the previous example when we saw the entire data set. So here is a no. And in this case, in the second case, if somebody was not a homeowner, although it's a mixed set of data records, the majority were not defaulted. So the answer will be no as well. Actually, so this is not really a big decision because no matter which direction we go, both will be no. But we have now already created one group which is pure in the sense that all class members are having the class binary membership that they are not defaulted. In the next step, we can see that we have added one more of our attributes, the marital status. And the marital status is actually having three different values which are possible. And we have decided here that we will go for a binary decision. If somebody is single and divorced, we will say that it's that then the person, if somebody is not a homeowner and it's single or divorced, then it's we are categorizing that person as a person who cannot repay the loan. While if they are married, then everything should be fine and they are safe to lend them the loan because they will be able to repay it. That will be the decision tree status at this point. And we can further grow it because we are still not done with this. Will be currently already a pure class, pure node with all records only consisting of class defaulted no. However, this single and divorced will still have a mixture with now, this time it will be the majority will be yes. So we will take actually, in fact, the last of our attributes we have, but we do not need to use all of the attributes in the other cases, but in this case we are, and we will be using this continuous variable where we are separating it to by some interval under 80K and above 80K, and we can see now we obtain pure class of defaulters, no defaulters, and above the 80K only defaulters. So in this case, we have all our nodes are having a pure class membership from the training record. And at this point, we stop growing our decision tree. So we stop when all records belong to the same class or all records have identical attribute values. So sometimes we might end up in the same attribute values for different records, and they might have a different class membership. But then based on the other attributes, we cannot distinguish that, and then we stop and take the majority vote. That can also sometimes happen, and it could be also attributed to the noise in the data. Let's have a look at what can we do with various type of attributes if we are taking them as being the one attribute which should decide what type of question at that level of the tree will be asked. So we can have a binary attribute, like for example, what was the homeowner status, for example, and then the binary attribute has basically just two possibilities, yes or no. Or in the case of body temperature, in case of the animal kingdom, it was either warm-blooded or cold-blooded. There was no other option. So this will be an complete, it is mutually exclusive, and it is exhaustive choices of the children from the node of the body temperatures. And that is useful for the binary attributes, and therefore binary attributes are very useful for decision trees in general. Then we have a nominal attribute, which is a categorical variable, which is not really a ordered in a way, but it has more than two categories. Like, for example, the marital status. We can have single, divorced, married. Actually, there are other marital statuses as widowed, for example, and all these could form as children of the nominal attribute. However, we can also decide that we go only for a binary tree representation, and in such a case, we can just group. Let's say married will be separate, and single and divorced will be together, or single is one category and the other category is married and or divorced, or we have the marital status single and married, and another category will be divorced. So we can choose any of these four options for having this ordinal attribute, the nominal attribute here. For the ordinal attribute, like for example, if we have t-shirt size, let's say small, middle, and large, we can proceed exactly in the same way as in the nominal case. We can either have a multi-way split, or we can have a binary split which will be then grouping maybe small and middle to one category and large to another category, or maybe large and middle to one category and small to another category. In this case of ordinal attribute, maybe it will make less sense to group S and L to one category and M to another category, but sometimes we can imagine that for some scenarios that might make sense. Let's have a look at what type of split strategies can we have for the continuous variable. Continuous variable as is having multiple possibilities because we actually have a continuous interval on which we can find a split. Well, we can find a binary split, like for example here we have an annual income of less or more than 80K, but we could also have a more multiple split of 5 different categories where we have one is less than 10K, another one is between 10K and 25K, another one is between 25K and 50K, and another one is between 50K and 80K, and the last one is then more than 80K. This could be also a way how we can perform this split. Generally, it makes sense to look at the annual income and perform some logical operation on it, like, for example, sorting, so that we are able to see how many of records have what type of values from this continuous variable. Let's discuss what would be a good strategy for choosing a measure to select the best split. So which variable would be the best to take next? So the measure typically, as we have already discussed, should somehow lead to reduction of impurity. So we can think of that if we have our entire training set, it is highly impure in terms of what type of classes does it represent, because it represents all possible classes of our training set. Now, if we take out some of these elements based on a good condition, we might split our training set into maybe two sets, while one set will become completely pure, perhaps, and the other set will be impure, but overall the one set will at least gain a lot of purity by that. So that could be a good strategy for a measure to select a best split. So in case we have two classes, fraction PIT, so that is are records which are belonging to class I at a given node T, should basically become smaller in the should become either zero, or it should be the maximum possible, and that would be considered in the children, and that would be considered as a good split strategy. So for two class problems, we can, for example, think that the pi of one class is 1 minus p0, while the p is a probability. This probability will be just one way to express the frequency, and it's in some sense the normalized frequency, where it is normalized against all the records at the node t. So imagine, let's have a look at the examples here, where we have a possible split in some kind of hypothetical example we don't know much detail about a gender. Originally, we have in our case, we have mixed gender, and we have when we divide based our hypothetical problem into males and females, for one condition, we don't know about that condition. It's not the gender condition. It's maybe the whether somebody will be able to repay the loan or not. So C0 will mean yes, they will be able to repay, and C1 no. And in women, in the case of women, 4 will be able to repay and 6 will be not able to repay. So the gender was not really very discriminative in case of uh, separating the case into number like a more purer children classes. Maybe in the beginning we had the situation where we had in total 10 men and 10 women here, and so it was like a 50-50 was the purity of the because they in total were able also to 10 of them were able to repay and 10 of them were not able to repay. So it was a highly impure node. And now based on gender, we have slightly reduced the impurity because we do not have a split 50-50, but 60-40 and 40-60%, let's say, or 0.6, 0.4 probability, 0.4 and 0.6 probability, but this is not a very good split. So if we have the same scenario, maybe it's about the loan application. If we are deciding based on the car type the individual is having instead of a gender, we might observe that those who have maybe the family car, one of them would be able to repay the loan and 3 of them would not. And maybe if we have a sports car, if you have a sports car, then you will be able to repay the loan and because there is everybody is just from the group that they can repay the loan, and nobody in this child will be from those who cannot repay the loan. And if you have a luxury car, then there is only one person who would be able to repay the loan and 7 who cannot in this hypothetical scenario, which might not sound very realistic, but it serves the purpose of explanation. So overall, if we look at this, we have the feeling that it is much more discriminative than the case of the genders. So the car type would be overall a better choice for an attribute in our decision tree because it is has a stronger expressive power in terms of classification. And if we look at the customer ID, then which might be a kind of different values, it's a continuous variable, then we have multi-split, and we can see that we can create some kind of a classification which will be only into pure classes, but there will be many. So this is from V1 to V20, so there will be 20 children. So all the actual customers will be sort of children, and this will be resulting in completely set of 20 pure classes. But this is not really a proper decision tree because it is highly overfitted, as we will be calling it in the next slides. Therefore, a decision for making a good impurity measure can be based on the various type of measures of impurity or purity. One of them is coming from information theory or also from thermodynamics, and it is called the entropy. Entropy, we have already seen it before, is formulated as a sum of all random variables and their probabilities and times logarithm of their probabilities. We will not go into the detail why this is the case, but here we will be going through all the elements which are here, all the classes within a particular node T, and we will be having the probability of that class. So that is the number of the element which belong to that particular class I divided by all elements of T. So that is the probability, the fraction, and here is the logarithm of that fraction. And we can see that the entropy here is basically calculated from this sum, and it has this is the function of entropy, this is the profile. So if you have a, uh, a probability of 0.5 between, let's say, two random variables, so both of them are equally likely. So this plot only shows plot if you have two random variables or two classes in our case. So if we have likely probability for both, that will result into very high entropy. And if you have a small probability for one, which means high probability for the other one, then you can see how the entropy is rapidly going down, and it's symmetric, going down on both sides in the same way, because in case of the two-class classification, we have the rule that probability of P1 is equal to 1 minus probability of P0. So we can see this probability measure in action, the entropy. So we have, for example, in the case if we have 0 elements out of 6 from the node, this will become 0. So this is 0. Logarithm of 0 is, well, will be minus infinity. However, we will or no, we will define it as this multiplication. This function has a continuity at 0, so this will be defined as this multiplication 0 times log 0 will be defined as 0, and then we have the 1 here, 6 divided by 6, and logarithm 1 will be 0, so this will be 0 as well. So we will have entropy 0 in case we have a highly pure class. Now let's have a look at the other measures. So here we have the so-called Gini impurity measure, which is 1 minus the sum of the squared class types. So let's have a look at what this measure is giving us in this case. Well, it is giving us the outcome is 1 minus 0 divided by 6 is 0, and 6 divided by 6 is 1, powered by 2 is 1, 1 minus 1 is 0. So it's the same. Here is actually the Gini type of function, which will be very useful for us. And then we have the misclassification error, which is just defined as 1 minus a maximum of these probabilities. So we have here 1 minus and 0 divided by 6, and 6 divided by 6 maximum is 1, and 1 minus 1 is 0. So that's if for the case if we have two-class classification, and in our node we have 0 of one class and 6 elements of the other class. If we have another scenario, so we have not completely pure node, but one element is there from the class 0, let's have a look how will this measure calculate that. So we have 1 minus 1/6 squared minus 5/6 squared. So this will total give us 0.278. This is somewhere here. And then we have for entropy, we will have a similar calculation. So 1/6 times log times 1/6 minus 5/6 times log 5/6 is 0.65, somewhere here at this point. And for the error, misclassification error, we will simply have 1 minus 5/6, which is 0.167. So we can see that all of these functions have the peak at the same position, and they are monotonic until that peak up, and then monotonic from there again. So it's basically they are all have the same profile, and we can choose any of those, and they will have a very similar performance. So in the case that we have 3 and 3, we can see that Gini will calculate 1 minus 3/6 squared minus 3/6 squared. So this is 0.5, 0.5, 0.25 squared, 0.25 plus 0.25 is 0.5, 1 minus 0.5 is 0.5. The same thing holds here, 1 minus one of these will be again 0.5, and we can see that the entropy will calculate us the value of 1, where we have 0.5 logarithm 0.5 plus 0. Or minus 0.5 times logarithm 0.5 in total will give us the value 1. Okay, so we can see that these measures will be able to give us good understanding of how pure one child node is. So this is just about one node, but we typically split, or always, if you like, the decision tree into several children, maybe most of the time into 2, but sometimes also into more than 2. So let's have a look. How can we measure the impurity reduction into when we decompose that group of records into the children nodes from the parent node? So that is can be expressed as an overall quality of attribute is the gain in purity by this decomposition into children, where I is here in this case the impurity measure, K is the number of attribute values, and Vj is the child node. So we can see here that our uh, purity measure is the impurity measure of the parent, which we have calculated, for example, by the Gini as in the last slide, and then we calculate the amount, the sum of the impurities of the child nodes, and each child node is multiplied by the amount of the elements in the child node divided by the overall amount of the whole number of elements in the parent node. Please note that this gain characteristic, if we use this function, but for the I we are using the entropy, this will be actually having a name as information gain from the information theory. So this is a well-known quantity, in fact, from information theory research. So if we are performing this type of calculation, we can see what happens in the case of this choice, which attribute we are taking, whether the attribute A or the attribute B in abstract terms. So here we have a situation where the C0 is represented by 6 records, C1 is represented by 6 records, and now in the case of A, we are performing the separation of into node N1, where we have suddenly 4 elements on one side of the class 0 and 3 elements of class 1. So we are changing this completely uniform impurity into a little bit more favoring the number of elements in class 0. And in the node 2, we will have the 2 of the class 2 and 3 of the class 3 elements of the class 1. So this is one possibility. And then what we can do here, we can calculate the sum of the children. So this expression is calculated here, and we can see that the purity gain has been um, in total 1 minus the, the impurity of the parent minus the impurity um, uh, uh, summed up and weighted and summed up in this sum. Now, once we subtract the Gini value of the parent from the Gini of the children, we will come up with a value which is almost zero, like 0.14, uh, uh, 0.0 14 will be basically the gain. So the gain will be very small. And therefore, we might want to also examine also what is happening with the attribute B. So in case of splitting here, we will find out that the impurity has been reduced more significantly because we have only one element in the group which has class 0 and 4 elements of class 1, and then 5 elements of class 0 and 2 elements of class 1. So this is much stronger purity, not completely, but stronger, and the Gini index overall will have a smaller number, which will mean that if we subtract this impurity index from the impurity of the parent, then we end up with much higher gain, which is then almost 1 order of magnitude better than the in the previous case. So therefore, we should choose the attribute B and not the attribute A for in the decision tree. And here we have another example where we can see that we have the various uh, categories or attributes, like car type is selected as sports luxury on one side of the binary tree and family on another side. And this will give us the Gini index of 0.468. And if we are performing other type of because we can see that the impurity has not here is almost very high, although here it's not that bad. It's still not ideal. If we separate the sports car, we isolate the sports cars, and we put together the family and luxury cars, then we can see that the Gini index is much smaller, so the gain, the purity gain, will be much higher for that for this type of children definition. And if we have all three separately, then we will see that this will lead to a Gini index which is even smaller. And it is natural because here we have aggregated two different values of the attribute, and therefore it naturally needs to lead to higher impurity, or at least the same. So by separating it into all three possible categories, we have the lowest possible impurity for this one categorical attribute. We can see here that actually our Gini index in sum is favoring separation to as many categories as possible. And that is something which is not ideal, and we need to check that how to limit the amount of children from a particular node, because we do not want to have nodes which would have thousands of children. That would not be a good design of a decision tree. So therefore, we need to focus this discussion particularly in the context of continuous variable, because in case of continuous variable, we can really have infinitely many splits, if you like, on an interval. And the idea would be that we do not have too many splits at least. We can have more than just two, but not too many more. And we need to somehow limit that amount of splits. So how to split a continuous variable? Let's have a look at that. We already discussed that it would be good idea, because if we have the annual income at this position here, we first want to have it somehow sorted, so that we can see how these values go, and then we can have various split positions, like, for example, a split position above and below 55,000, but that will actually lead to Gini index for 20, because we will have one group which is actually not having any of the records, and the other group will have all of them, because this is less than the smallest average annual, than the annual salary. Then if we go to 65, we isolate the one entry with 60, and we will see that the Gini index has been reduced, which is then beneficial partially, or better than the previous split. Let's have a look at how this continues. If we perform another split, which will be at the value 72, we will further reduce the Gini index. If we perform the split in at 80, we have again a lower Gini index, but then we are increasing. 87 is for 17, and then we find out that if we should have a binary split, then the binary split at the value 97 would be giving us the highest, the smallest Gini index, so resulting in the highest purity among the children. So then we see how this further develops, and then at the end we again have all of them above 220. If we have our split value, then all the elements are in just one child and 0 in the other child. So this is a strategy which we can follow to find, if we sort all of these values, we can just go one by one and see how does the Gini index is changing for a binary split. However, this will lead to having to calculate it between a lot of records, and this might not be very efficient. So therefore, what actually makes most sense is to calculate the binary split where between the records where the class label changes. So for example, here the class label was changing, so that would make sense to have the 80 as a value for the threshold for this continuous variable. And then the next value has changed between the 95 and 100. And that was actually leading to our best value. So actually, we just need to check at two different positions in order to find out what will be the best binary split. And the reason is that if we are having this sorting, and then we are having a change of some kind of the class membership, then it means that we will be just at the border, and we will maximize somehow the amount of members on one side, and minimize that amount on the another side. So this is a good optimization, just to evaluate it at the intervals where the split will cause that there is one value is one class, and another class membership is a different one. So which is then here and then here. For binary split, we choose the split with the highest gain. For multi-way split, we choose several splits that maximize the gain, And we will not talk about strategies how this could be done because that could be a more complicated approach. However, overall, our splitting strategy with Gini or the other ones will in general favor to have many child nodes, as many as possible. And we don't want that, we already said. So therefore, we will create a slightly different gain ratio, which will be penalized by here the entropy value of the entire uh, set of children. So this is a probability of a child, or the amount of elements in the child divided by the all elements in the parent. This will cause this form this probability value, which we will have here, and the sum will become high if we have a lot of children, and this will lower the gain. So the more children we have, the lower this gain will be, and therefore it will be penalizing naturally the amount of children which we had uh, chosen as splits, and will keep the number of splits in reasonable bounds. So now we understand how can we design a decision tree, because we know that we have to simply just go with this in this recursive manner through the nodes, and at the same time just use a one of the variables for making a decision, and choose the variable which creates the highest purity gain among the remaining data records during the training process. So that is basically it, how it should be designed. And then once it's built, then we know how to perform the classification. We simply let the record traverse through the decision tree, and based on its own attributes, it will find the leaf based on which one it will be classified. So, a couple of interesting remarks about the decision tree is that decision trees are non-parametric approach to build a classification model. We didn't have any parameter like we had the parameter k for the case of the k and n classification. We can we Finding an optimal decision tree is an NP complete problem, so we might not end up in the best decision tree when we are performing the design, uh, and so but it might still be good enough for our classification task. Building a decision tree is computationally not very expensive, and the classification process for new data entries is very fast. Smaller decision trees are actually easy to interpret by humans, and that is very because the answer of classification membership is basically established by some kind of dialogue as which is created as the entry is passing through the tree to its respective leaf node. So it is easy to understand why something was classified into that category based on its property values or attribute values. This is not the case for other classification schemes, like, for example, neural networks, where this is entirely a black box approach of classification. We would be talking about the white box classification techniques, and the decision trees are clearly representative of that category. Now, if we have the redundant attributes in the case of decision trees, that is not really a problem, because those might not be chosen for the decision tree. One of them will be chosen, the one which is the most expressive, or actually any of them, and then that one will be used for the making the decision and for the purification of the training data records. So we can have a problem with data fragmentation if we run into the problem that we have leaf nodes with too few elements inside. So that would clearly have a consequence that we are somehow having a kind of an overfit. If we will have just one element in each leaf node, that will be clearly an overfitting, and few this will mean essentially the same thing. Now, another problem which might occur, and it's not really a problem, but it's kind of less efficient, and the decision tree is unnecessarily complex, is that in one particular subtree, if we are choosing an attribute, that attribute is chosen among all attributes which hasn't been used until on the current root, if you like. That might mean that in other subtree, we might as well choose the same attribute. And we might, during the buildup, actually create the same type of structure several times. And this might mean that we are creating the decision tree unnecessarily doing the same calculations, and also that we are making the decision tree unnecessarily complex. So if possible, it would be good to avoid replication of subtrees in the decision trees. One aspect which is important and relates to our previous discussion of the KNNs, where the KNNs had as their, or at least the nearest neighbor, one NNs were having as the decision boundary arbitrary geometry of this Voronoi tessellation. In case of the decision boundaries of decision trees, we can see that we have actually just a rectilinear boundaries. So our decision tree will be having this kind of shape, if you like. So here you can see all the categories, and it has just created 4 rectangles out of this one big rectangle to categorize the different categories. We can see the decision tree being here based on this categorical, these continuous variables x and y. And while this is a good decision tree, it is not able to create us some kind of oblique type of decision. Therefore, there has been an extension of decision trees which are able to perform also diagonal splits, and those are oblique decision trees, and they do not then involve a single attribute in their node, but will have several attributes somehow expressed in their nodes. So there will be more of a, like a rule, mathematical formula will be forming the decision. And in such a case, we can create a decision boundary which will be diagonal. So, and those trees we will not be covering in more detail. I just wanted to inform you that such extensions of the decision trees already exist. After we have become familiar with various types of classification schemes, such as KNNs or the rule-based classifiers or the decision trees, let's turn our discussion to analyzing some characteristics of models themselves. So classification models can be evaluated by a training error, but also by the so-called generalization error, and both must be allowed. So the training error is an error which can be measured by analyzing how well does the classification method perform on the training set itself. Ideally, this measure is low, and also However, also generalization error is low. And what does this generalization error mean? It is the error which is measured from data records which have not been part of the training process. So that could be called the validation set or the test set. And this generalization error must be low for these, especially because we want that we are able to classify objects which previously we didn't know the classes of, and now we can automatically assign the classes to these unclassified data records. So, and here we have several phenomena which can occur during the training and which influence this generalization error and also the training error, such as, for example, the model overfitting or underfitting occurs during the training when in case of overfitting, when the model fits the training data too well, but the generalization error becomes high. We can see that on the following example here. Here is a mixture of two distributions, one random distribution and one distribution of three Gaussian of a Gaussian mixture model, and we can see the data here becoming the circles and the crosses here. Now we want to be able to classify a new record, whether it is a circle or it is with high likelihood a cross. And as you can see, this is a very tough task here. If we do not know about their underlying distributions, which I just mentioned to you, then this becomes quite hard. Nevertheless, it is possible to establish this relationship by training based on this training data. And we can see that from the initial case when we started the training and generated now for ourselves the decision tree based on the positions within the X1 and X2, we can see that the training error is becoming now smaller and smaller with um, with the width I mean with the size of the decision tree. So the decision tree is increasing and the error is rapidly decreasing until this point, and everything before here we can consider as a so-called underfitting. So if we will be at this position with this error, our decision tree is not expanded sufficiently that it can perform the classification task well, and further training will improve it. But at some point, the model starts to overfit to individual elements. Imagine that we can, if we draw a small little boundary around every of these points, of these training points, we will end up with a perfect training decision tree, which is characterized here. So in our case, if we have a decision tree, we will be drawing a small rectangular areas around every of these data points. And with that, we could reduce uh, the error, the training error, or to zero, pretty much. And but we will end up with almost 250 nodes for the decision tree. Now, to that, if we will add a new point, new test point, we will with high likelihood wrongly actually classify it, because we have heavily overfitted our classifier to the training set, and all the new points are not really considered. And we can see that on the validation or test error, where we have been here closely following the test error was following the training error, but at this point the overfitting started, And we can observe that our test error, not only that it doesn't go down, it actually increases and becomes worse and worse. So this is an example of an overfitting of in this case, decision tree a classifier. But overfitting is a phenomenon which happens to, which might happen to every training of any type of classification technique which uses an distinct representation for performing the classification task. So, and what is the reason for overfitting? Overfitting can originate from for various reasons, and one of them could be, for example, noise. Imagine that we have um, a certain noise in our training data, meaning that we have some classifications which are not perfect. Like, for example, here we can see that that the bat is a warm-blooded animal. It does give birth. It's not four-legged, but it has been wrongly classified that it is not a mammal. And similarly here, a whale. So in this case, we have a wrong, some errors, few errors in this training data, which is reasonably common in the data sets, real world data sets, that there is some error. Now imagine that if we use, based on this, our classification scheme here, we can perform a classification which will actually end up in classifying the mammals into, according to the body temperature, warm-blooded, gives birth, yes, and then four-legged, yes, mammals, and no mammals, which is not true. But here we see that there are just two examples of non-four-legged mammals, and both of them have been subject to this noise, to this error, and they have caused that this decision tree grew to such a detail which no longer was covering the truth. So we can see here that this would be a more accurate representation of the decision tree, which, if we would prune this depth detail, we will get an accurate assessment, and our, for example, human will be correctly classified as a mammal, while with this decision tree, it will not. So for some training models with higher training error but smaller generalization error, those small models are performing better. So so it is not necessarily the case that if we have a higher training error that we have a worse model. Actually, what is the guidance is the smaller generalization error. And as you can see here, in this case, the overfitting can originate from the noise, as was the case here. Fitting can also arise through lack of representative samples. So we might have in our training set some samples which will not be very representative. So for example, we will be interested in performing a classification of which animal is a mammal again, and here our training set consists of salamander, guppy, eagle, Urwil, and platypus. And out of these, only one is the actual mammal. And even that, platypus is not really a standard mammal because it doesn't give birth. So given this data set and given this data entry, if we build the decision tree, we can see that the warm-blooded determines the likelihood of being a mammal, and then it hibernates, So this is already very strange because typically the mammals do not hibernate, maybe with few exceptions, as for example the platypus here. But then if it's not hibernating, it's not a mammal, which would be already wrong. Four-legged will be also if it is, then it's a mammal, but only if it hibernates. And if it will be not four-legged, then it will not be a mammal. So there are several problems with this decision tree arising from the fact that we do not have representative samples on which the decision tree can actually make a proper decision what rules hold for most, if not all, the mammals. If we now look at the model which is generated, and we would like to assess its how good it is, just give a rough estimate of that, one can think of that the assessing the training error could be a good estimate for the model performance. And maybe to some degree it is a good first thought, but actually we can see here, if we compare a training error which goes to 0 and a test error which goes constant even with the complexity of the decision trees. So after we had, I don't know, maybe 5 decision tree branches, so the depth of roughly 3, we started to deviate between the test error and the training error. So overall, we see that in this particular case, we are not very good in having a good estimate of the actual model performance by this training error, because test error is telling us a completely different story. This story is about classification, where we want to classify the samples based on to which class do they belong to, the blue class here or the red class. And we can see that an initial decision tree has been created, which is actually here at exactly the point of where the deviation between the training error and the test error started. Then we can see that we have basically just 1, 2, 3, 4 nodes, or we have which are intermediate, or 1, 2, 3, 4, 5 leaf nodes to decide on the position. And if we look here, we can see geometrically actually nicely how does this decision tree look like. And we can see that the classification for the blue points, and here the blue color of the training error and the red color have nothing to do with this coloring here, so that's just pure coincidence. This blue color here points are centered around here, and our decision tree has decided that whatever is inside this rectangle will be most likely the blue class of little pluses, while everything else will be regarded as the other class of the red circles. Now we can see what happens once we have a lot of once we are, let's say, somewhere here, maybe 50, 60 of nodes. We can see that actually this our model is heavily overfitting to some noisy placement. So we can see that this spread is not very abrupt. There is a smooth transition between the blue class of being represented, and you can see that these kind of decision trees are trying to follow even these kind of outliers, which are a little bit more far away from the center of this classification class. So that is something which has been clearly overfitted by this decision tree, and that will lead to actually a low performance. And we can say that model complexity has an impact on overfitting, and we should try to keep the model complexity as simple as possible, because every more higher complexity we add to the model, we are risking that we are overfitting to noise and to outliers. So therefore, our model should be as simple as possible, and therefore during the build-up of the decision tree, we should actually somehow punish the model complexity so that it doesn't generate us an overfitted result like we can see here. So the approach how this can be done can be using the so-called Occam's razor, which is an approach where given two models with the same generalization, with the same generalization error, a simpler model is preferred. That's the principle of this Occam's razor, and to that closely related is the so-called pessimistic error estimate. So we had the optimistic error estimate, and that was saying that the training error is an estimate for model performance, and the pessimistic error estimate is that we are adding and we are somehow punishing or penalizing the model complexity. So pessimistic error estimates of a decision tree T with n T being the number of training records classified by the node T, where K is the number of leaves, and ET is the overall training error, and NT is the number of training records at the of the entire entire training data, and then omega Ti is the penalty associated with the node Ti. So the pessimistic error estimate here for actually the Gini, we can say, is that we sum up all these errors which are associated with wrong classification at the node Ti, so which will be wrongly classified as a different class, plus the actual penalty of the model complexity. So this penalty can be associated like with every node we expand, we will have one more. With every leaf node, we will penalize the linearly with the leaf node growth, and then we divide it by this total number of children of this current node over all the classes which these leaves children are split into, and this is equal to an overall error of the tree divided plus the model complexity penalty of the tree divided by overall number of the number of training records. So let's have a look at this on an example how this error can incorporate these penalty terms which are expressed here, penalizing the model complexity. We have here two different decision trees where these decision trees, the error of the tree on the left side is equal to 4 divided by 24. So this is, we can see in this case that there will be some 4 misclassified entries in the training set out of 24 entries. So this is the error which is not yet penalizing the model complexity. And then we have another tree which has this error rate which says it's 6 divided by 24. There are 6 of these elements which are misclassified here. So okay, so that's a misclassification ratio here, which we can observe also from this tree here. So if we look at here we have 5 and 0, so here is no misclassification possible really in the training set. Here we have 1 misclassification, so it's always the smaller number. Here we have 0, so that's fine. Here we have also 1, so that's 2. And then we have here 1 and 1. So we have in total for these 3 we have 4 misclassification. And for these 3, if we look at it, we have here 2, here we have 1, so that's in total how much? That's 3, and here we have nothing, and here we have 3, so it's in total 6. And if we now look at these two models, one is much more complex than the other one, and here we have the model complexity penalty of 1, which basically just sums up the total amount of our leaf nodes, like 1, 2, 3, 4, 5, 6, 7. So it's 7 times 1. It's actually coming into this error rate for this error of the pessimistic estimate, and in total that will be the error weighted by the model complexity or penalized by it 0.458. And then in this case we will have, although we have a higher error of this tree, but it's a very simple tree, so the model complexity is very low, and that will lead to slightly lower error rate, which takes the model complexity into account, and this model will be then preferred eventually. So this is the way how we can incorporate the model complexity into the error rate estimate of our decision tree buildup, and with that we can prevent it to grow into extents where it will be largely overfitting to the training set and to the noise within the training set. So there are several ways how we can handle the overfitting. First of all, we can have our data separated into various sets. So generally, what currently is being done in terms of model training, we will have 3 sets. One set is the training set, another one is the validation set, and one is the test set. The training set is used for training as before and contains most of the data. Then we have the validation set, which is used to test the validation error. How does the model generalize? And with this validation set, we can set certain hyperparameters. If our model has certain hyperparameters to tune, we can use the validation set on tuning these hyperparameters. So it is not used for training the model, but it is used for setting the hyperparameters, like for example, how big penalty should we give to what should be the penalty score for the model growth, for example. And the last set will be the test set, with which we will do the final evaluation of the model at the very end, once it is trained and hyper-tuned, and it's ready to be tested by data it has never seen before. That is one strategy how we can handle overfitting. Another strategy how we can handle overfitting, because this validation set will be, once the validation error will be high, then it will stop the training at the early stage before it starts to the model align to the noise. And then the next type of method which can be used for the model overfitting is the pre-pruning. So we can, before we decide that we are growing a tree, we stop expanding it if the gain from impurity loss is below a certain threshold. So we will have our choice to make which attribute to use. But even if we choose the best one and the impurity loss or purity gain is below certain threshold, then we might decide that this is not worth it, and we will not even expand into child nodes. And that is called pre-pruning. In the case of post-pruning, we first let the decision tree to grow to the maximum size, and then we will start from the leaves and start the pruning process bottom up for the decision tree. And if the generalization improves after trimming, we replace the subtree by a leaf node. So we can always see whether the generalization error is performing better after we perform certain merge or deletion of a subtree. And if it does, then we will prune this part of the decision tree to improve the generalization error. We can think of a strategy how to choose the best model. And the best model choice could be done in such a way that we take our entire data we have available, split it into part which is the training data and which is the test data, and then by the method of the holdout, so we hold some data for the test, and then we simply run and build the model. And even if it's not prone to overfitting, we will simply just store that model, and then we will take another time the same data, split it differently than we split it before, and then we will again perform this training and test it with the new set within that available data we had. While having the test data always reduces the amount of training data, because we need to have this ground truth data available from somewhere, and we take it from the entire pool, so our training data has to be then naturally smaller. It helps us to be able to understand which model is performing better. And then we can several times perform this model training so that we are always dividing our data between test data and the training data, and then we create the model, and then we evaluate whether it is with the evaluation measures of which we talked about before, like the accuracy or error rate, whether it is better or worse than any other model. And then after several rounds of this process, we can choose the model which is performing the best. A similar strategy, which is slightly different but in the same spirit, is the model evaluation performance of the model using cross-validation. Cross-validation, in that case, each record is used exactly the same number of times for training and once for testing. So we can have a twofold cross-validation where we will have half of the data used for training and half of the data used for testing, and then we will create a model and evaluate that model performance, and then we will perform the model performance evaluation when we swap the roles. So the same part which was previously used for testing will be the training data, and the part which was for the training data will be used for testing. And this is entirely fine, because never when we create the model will see actually the test data before the actual test. So it's not trained on that. And this is a twofold cross-validation when we have the same training data used once and the test data also used once. But then we have k-fold cross-validation, and that is an approach where we partition the data into several categories, so like a subset 1, subset 2, and subset 3. And so it's a threefold cross-validation in this case. We partition the data into 3 partitions and train k-1 models. So in this case, we will be training one model in this case, another model in this case, and another model in the third case. So so actually this should be k models here, as we can see. So we can train with k-fold cross-validation k models. So we train here, like for example, 3 models, and then we evaluate. So once this is a test set and here is a training set, we train one model, then we have this and this being the training set, and this is the test set, we train another model, and here is another case where we have this as a train set and this is a test set, and we train these 3 models, and the which one performs the best, we can choose. So there is an approach which works well. The disadvantage is that we have to train a lot of models before we choose the best one. There is a specific case of the k-fold cross-validation, which is called leave one out, and that means that the k is actually the partitions into n, so which means that we partition the data into the entire data set, so that training set will be all the data records minus 1, and then but this leads to many models to train if we have a lot of training records. So this can be only done in case we actually have a very few records, and then we will just use one record for the testing using the cross-validation leave one out method. This, we are concluding the lecture on the classification seen from the data mining perspective, where we had used or looked at the classification principles on the principles of various classification methods, such as the KNN or the rule-based classification or decision trees, and we specifically in these cases looked at those classifiers which are not probabilistic. In machine learning classes or course, we will look more at the probabilistic classification methods, and therefore we wanted to focus in this class on those which are not based on probability theory and statistics, but are more based on rule-based approaches, and also in some sense are therefore easier to interpret. So this is the conclusion of the classification lecture, and I will see you on the next lecture about data mining techniques.